Okay, let's continue our studies. So last time we discussed quantum BFV systems. Well, often people say BFV-BRST, which is historically is more proper, but just for short I keep this to be concise systems. So this means that we have a algebra of operator algebra, we have a representation space, everything is graded, we have BRST operator, an element, distinguished element of this algebra, and we have our Hamiltonian, which is also an element of, maybe we should close, otherwise it's too, also element of our algebra. So this data defines for us quantum BFV system. Then we can say that physical states sit in cohomology of our omega in degree 0 in our space, and observables and equivalent observables. This is cohomology of a joint action of our differential in our algebra. And there are simple exercises to make sure, which were exercises I gave last time, that this space is a modulo over this algebra. This is itself an algebra. Right? So somehow in degree 0 we recover our physical system, which is hidden in this big system where on top of, let's say, physical degrees of freedom, there are some auxiliary variables like pure gauge variables, ghost variables, and etc. Okay, then we discussed irreducible representations, Irreps of this BRST algebra. And if we don't pay attention to Hermitian inner product on our representation space and forget about the fact that omega must be Hermitian, then there are two guys like this, right? There are singlets, so it's a one-dimensional space with a basis element E, such that omega E is 0, right? So this is like a basis in cohomology. And second, there are null doublets. These are also known as contractible pairs, two vectors F and G, such that always hat omega hat on F gives G. From this, it follows that G is in the kernel of omega hat, right? So this is nothing but picking a basis consisting of such E, F, and G means just bringing to Jordan form the matrix of our operator omega hat. Then life becomes slightly more interesting when we recall that there is an inner product on our representation space. It has certain degree. For definiteness, let's say that it is minus k, because we can't necessarily make it 0. And then we have a bit more options. So in addition to singlets, null doublets, in this case, on this space generated by these two vectors, there should be non-degenerate inner product, and of course it must be the one for which f and g are produce something non-vanishing, right? And in addition to this, there are non-null doublets and quartets. So now I want to give a couple of examples which I mentioned previous time, but I think it's worth spending a few more minutes on this. So the first example is, let's take H to be polynomials in ghost variables, so just two-dimensional linear space with the basis 1 and C. C is a ghost, so ghost of C equal to 1. And this is tensored with a genuine Hilbert space. And the inner product on this H is taken to be integral dc, and then inner product on our space V. Let me denote it with not for short. So this is a Hilbert space. On this Hilbert space, we have an inner product denoted like this, and then we extend it to our entire representation space, which is this tensor product, right? And this is Berezin integral over the ghost variable C. So, for instance, in this case, ghost of our inner product equals what? +1. So degree of C is 1. This is a formula. So I substitute. So because it's a tensor product, right? I evaluate this, and then I take integral over C. So what is the ghost degree of this inner product? -1, right? Because this integral like kills 1C, so lowers the degree by 1. So this is -1. Yeah, that's quite a typical situation. Okay, so let's see what this. How can we decompose our representation space into irreducible representations, and what they are going to look like? So for this, so omega in this case may only have such a form, and we assume that T dagger equals T, so that omega is self-adjoint. And it's very easy to compute cohomology abstractly. So we diagonalize T, it's a Hermitian operator, it can be diagonalized. So we pick a basis consisting on vectors EI and vectors in V naught EI and vectors, let's say, H alpha, such that T on EI, these are vectors which have 0 eigenvalues with respect to T, and H alpha have some non-vanishing eigenvalues. So it's an orthonormal basis of eigenvectors for Hermitian operator T.
Basis
in V. For the moment, I'm talking about V because T acts in V. So this part from this factor is here. But good question, thanks. It has to be clarified. And T acting on H alpha is some K alpha H alpha, where K alpha is in R, without 0, right? So that's some non-vanishing real numbers. Then it's easy to compute cohomology, right? So what cohomology is given by? For sure, so what are states associated to this? So we have EI and we have CEI. Both are going to be in the kernel, right? Because T kills E. So if we go with omega on this guy, we get 0. But on this, we obviously get 0 because we already have C here, and here there is an extra C. But also, this guy can't be in the image because it's tempted to say that it is something like omega acting on something, but E can't be in the image of T. So it's cohomology. So what we get that, for instance, E1, C E1, the linear span of it is what is in our classification is non-null is not doublet. Let's do short, skip non-null. So it's a doublet, right? So this is a two-dimensional subspace, which can be identified with cogomology, with an inner product between these two is non-vanishing, right? Because integral over C precisely kills the C, and it's on orthonormal basis. So E1 with E1 0 gives me 1. So it's a doublet.
Sir,
Yep.
Again, what does this subscript 0 means?
Subscript here.
Yes.
So I form an inner product out of standard inner product in this Hilbert space, and also standard inner product in C space. So Z0 inner product with 0 is an inner product here, and inner product here I do explicitly as an integral over dc.
So if elements are C dependent, we first integrate on C and then use just our regular inner product.
Well, other way around, but I would do it other way around. I would first evaluate this inner product. C is like coefficient, right? So you get a function in C, and then you integrate, you get number. So, for instance, if there are questions, for instance, we have, well, let's calculate inner product precisely of these two guys, right? So we want inner product of E1 with CE1. By definition, it is integral over dc, right? By linearity, because it's a tensor product, C goes off, then we get inner, so this is just dc, C, inner product of E1, E1, and here we put 0, right? But this is 1, so this is 1. So we get doublet, which is non-null doublet, in contrast to null doublets, which we are going to hit immediately. And then let's see what happens with remaining states. So then it turns out that the linear span of H alpha and C H alpha, I put C here not to confuse with inner product, it's a linear span over complex numbers. So this linear span is a two-dimensional space, and it's irrep, of course, right? Because omega acting on this will produce a multiple of this, right? At the same time, the inner product is of these guys is again just integral dc C H alpha, and this is again 1, right? So we get two-dimensional space, which is not in cogomology. This is contractible because omega on H alpha equals to K alpha CH alpha, right? So these are two vectors. They are omega act on one gives another one. So this is null doublet. And there is an non-degenerate inner product, and one can check if, I'm not sure, maybe one should be a bit more careful with coefficients, that omega can be made Hermitian with respect to this inner product. That's what I didn't check. So this is null doublet. Null in the sense that it does not contribute to cogomology, but this is historical terminology. It's not used so often nowadays, but in the literature you can find it. Okay, so the story is about how the action of omega is compatible with the inner product. So if you are interested in pseudo-unitary irreducible representation, so subspaces closed under the action of omega, subspaces in the sense of, in the graded sense, so it's a graded subspace of a graded space, and omega is Hermitian there. Then we get now we have an example, two examples of such irreducible representations. One non-trivial, which is doublet, which is in cogomology, and one which is, let's say, physically trivial, so-called null doublet. Okay, good. Then next example is to demonstrate quartets, which is very typical example for which you meet in when you study like spinning particles, strings, or even field theories. What it looks like. It's like a toy model, but it's very typical. Toy model, trivial system. So suppose that we have two pairs of oscillators which look like this. A plus A minus dagger equal 1. So our algebra is generated by the following variables. It's like creation and annihilation operators. Then we have A minus A plus dagger. That's equals 1. And the rest is the relations which are not written are 0. And then we also have two pairs of ghosts. So we have C B dagger equal 1. And we have B C dagger. If I remember correctly, it should be minus here because of degree. Okay. And then, and the ghost degree is like this. So these are in ghost degree 0, and ghost of C is 1, ghost of B is minus 1, and dagger denote how the Hermitian conjugation goes. So B dagger also has degree minus 1, of course. Okay, good. And then consider the following. Consider the following BRST operator on this in this small algebra generated by these operators. So let's take omega, which equals to C dagger A minus or plus C A minus dagger. Yeah, something like this, right? So it's clearly Hermitian, right? If we act with dagger, we check it. It's clearly nilpotent because C is fermionic, C dagger is fermionic, and they commute, and these two A minus and A minus dagger also commute, so it's the simplest possible BRST operator with like two constraints, but it's immediately quantum, so strictly speaking I should put hat on top of omega. And let's pick our representation space to see how it acts. Representation space we take to be a just Fock space, usual Fock space, which is defined like this. There is a vacuum which is annihilated by all operators without dagger are considered as annihilation operators, and operators with dagger are considered as creation. So what we want that A plus minus C B acting on vacuum gives 0, and other guys create states. That's the usual Fock space construction, right? So, and this H can be identified with polynomials because any state can be written like certain combination of operators with daggers acting on vacuum. They all commute, all operators with daggers commute to one another. So we can just act with a polynomial in them on 0 on vacuum and produce a state. So there is a one-to-one correspondence between polynomials in these oscillators with dagger and states of this Fock space. So we have here A plus minus dagger, C dagger, B dagger. So this is our our space, and omega hat act in our space if we treat it, if we identify our space as polynomials, as a differential operator, right? Which is what? So A minus, C dagger, A minus, look here, is something like d over d A plus dagger, right? It acts like this, because when we go with this operator through this, we get 1, so it's like derivative. And then C is d over d B dagger, right?
Left derivative.
Pardon?
Is it left derivative?
Let's say right. Well, this is bosonic, it doesn't matter.
For C it doesn't.
It does, yeah. So let's assume that it acts from the left. So d over d, what is here, C, so d over d B dagger. And then we have A dagger minus. Well, better write it here, A dagger minus. Yeah. So that's what the action of this omega on our representation space look like. And it, of course, reminds us, it looks very similar to something like the Ram or Koszul differential, right? So there is a derivative with respect to bosonic variable multiplied by fermionic variable, like associated to it. And here it's other way around. There is a derivative with respect to fermionic variable multiplied by associated bosonic variable. So perhaps we can just repeat the standard argument, and we can make sure that homology of this operator is concentrated in. So actually, there is only one non-trivial cohomology class, which is which is represented by constants, right? Because whatever else is either killed by this operator or in the image of this operator. It's exactly like Poincare lemma in differential geometry, right? For the Ram differential, it's almost like the Ram differential. Think of this. The only thing that there is this twist of the parity. So this is like coordinate, and this is like associated differential form, and this is like a basis differential form, and this is like odd Grassmann-odd coordinate and associated basis differential, which is even. But still, the proof doesn't change. Actually, it's easy to prove that cohomology of the thing is given just by constants, right? So in fact, if let me. Is it clear, or should I give some comments?
If you kind of reason.
Yeah, so the simplest way to prove this is to introduce let me write it differently, it will be easier for me. So let's write like this. So we have, so that it looks like more like the Ram differential. So let's write it like this: theta I d over dxi. But x can be also fermionic, and degree of theta is a shift by 1 of degree of x. It's of course this form, right? x1 is A dagger dagger, x2 is B dagger, and theta 1 is C dagger, theta 2 is A minus dagger. So it's operator of this form. So how do we prove Poincare lemma algebraically in the space of polynomials? The simplest thing is to introduce the following operator n, which just counts the total number of variables theta I d over d theta I plus xi d over dxi. So this just counts total homogeneity in theta and x, right? Moreover, our D preserves this homogeneity. So it's enough to consider a subspace where n has a certain eigenvalue, right? So it's enough to consider elements such that n psi equals to some small n psi, right? and n must be integer because this is homogeneity of polynomials. Okay, so let's concentrate on this subspace, because if we prove it in one subspace but for generic n, it means that we proved it everywhere, that cogomology is empty but constants. Okay, then we introduce another operator, which is delta, which looks like this: xi d over d theta I. It's like other way around. Sometimes it's called contracting homotopy for some reasons. Then we observe the following simple relation. So anti-commutator, because these operators of they are odd, they are of degree 1 or minus 1. So the commutator is graded commutator. So we commute d with delta in a graded sense, which means that it is d delta plus delta d, not minus, plus, because they are both Grassmann odd. And what we get here, what is the answer? So d delta, what is their graded commutator?
On the subspace? Or in general?
Well, both. In this case, it doesn't matter. N, yeah, exactly, n. And if you're in subspace, this is just a number, right? Okay. Then, having understood this, suppose that we have a cocycle. So d acting on element psi equals to 1. Then we can do the following trick. And suppose that n on psi is in psi. So it belongs to an eigenspace with eigenvalue n of this counting operator. Then we can do the following trick. We can say, okay, we can write psi equals to 1 over n if n, assume that n is non-zero, is 1 over n, and then we can write Что?
Долго занятия будут? Вы только начали?
Да, практически. Что такое?
У нас с аудиторией накладка. Пришел человек, не знаю, куда его посадить. А если я посажу в переговорку?
Посадите, посадите. Mm-hmm. Okay, so if we have psi which is a cocycle, which is like this, then we can write it like this, right? But now remember this and this. So we represent n as an anti-commutator. This term gives 0 because d kills psi. So we get 1 over n d delta psi. And if n is non-zero, then it is just d on 1 over n delta psi, right? So if n is non-zero, it means that any element in the kernel of D is in the image of D, right? So that's the simplest proof of Poincaré lemma in, let's say, algebraic setup. In smooth setup, it's slightly more, one has to be slightly more careful. But in algebra, we said that this is a Fock space, which means that we generated, our states are polynomials, so it's perfectly legitimate. We don't need to discuss any functional issues. And so what we see, that if we restrict to an eigen subspace with homogeneity with n non-vanishing, then there is no cogomology. So the only cogomology is when n equals 0. But n equals 0, it means that we are dealing with a constant, right? So if we have d acting on constant is of course 0, and constant can be represented as a result because image of d must be proportional to theta. So this is a very standard proof. You can find it whatever. It can be in slightly different terms, but you can find it in many, many places. So it's worth spending a bit of time to play with it and to understand how it works. Actually, it's very simple and natural, and it illustrates the important technique. It's a particular case of important techniques from homological algebra. Okay, so what we just learned, we learned that our operator omega, all states are trivial, all cocycles are trivial, except for vacuum, right? Because vacuum is the only one where our operator n produces 0, right? So it's a state, it's in our Fock space, it's a polynomial which is just constant. So this is the only cohomology class. And what it has to do with quartets. Okay, let's give an explicit example of quartet. So we consider the following 4 states. We consider A plus dagger, A minus dagger, C dagger, and B dagger. Remember that we can identify states with polynomials. So we have consider just degree 1, homogeneity 1 polynomials. These 4. So what do we have? Let's first of all our omega acting on, this is our omega, on A plus dagger gives us what? Gives us C dagger. So acting on this state, we get this state. Acting on B dagger, sorry, B dagger, right? Acting on B dagger, we get what? We get A minus dagger. So acting on this state, we get this state. And of course, acting on this and that, we get 0, just because omega is nilpotent. So we have 4-dimensional subspace consisting of 2 pairs, which are like contracted by omega. And let's compute inner products. So let's compute A dagger with plus dagger, A minus dagger. Look at these relations. So we conjugate this, it becomes A minus, and A minus with A dagger is 1, so we get 1. So this is 1, and same here. So if we compute inner product between C dagger and B dagger, what we get, we conjugate B dagger, it becomes B, and we get here, well, minus 1 if I'm not mistaken with the sign, and the remaining, it's clear that the remaining inner products are 0. So this is precisely quartet. Right? So it's 4-dimensional space, 4-dimensional reducible representation of BRST algebra, and which is trivial in the sense that it doesn't contain cohomology. If you compute cohomology of omega hat, is 0, right? And in fact, all the representation space, all our H, decomposes. So maybe let me formulate it as an exercise. H is a direct sum of, let's say, 1-dimensional space on vacuum, or just 1 in our, because vacuum is 1, linear span of 1, plus quartets. This is the simplest one, which we find at level, let's say, at level 1. Level means the value of this operator n. How many operators we used to produce our state. So it's a homogeneity degree of our polynomial. So at level 0 we have singlet, which is just our vacuum. It's the only cohomology, 1-dimensional space. And then we have infinite number of quartets. All of them are trivial in cohomology. And all of them look more or less like this. The lowest one, at degree 1, I just explicitly showed you. This is very typical situation in when we use this BRST quantization in particle models and field theoretical models. I'll show where this index plus and minus come from. In fact, it's not for nothing I call this index down. Plus and minus, these are precisely the light cone indices if you want something covariant. Okay, and the next example, well, it's not really example, it's a toy model which is quite instructive of already a non-trivial, still very simple, but not entirely trivial constraint system, quantum constraint system in this BFV formalism, which can be used also to describe free fields, free gauge fields. So what it looks like this. So we have a Minkowski space, let's say M4 for definiteness, but it can be generic dimension. And then we have X mu, P mu. Immediately think of operators. They don't give a classical limit because you can always take it. And P, to avoid imaginary units, I assume that P is already multiplied by imaginary units, so this is minus delta mu nu. And this is commutator. So it's an anti-Hermitian momenta operator. Okay, and then there are fermionic oscillators which satisfy the following relations. So it's theta mu, theta dagger nu equal to delta mu nu. And we have some ghosts. So we have ghost C naught B naught, which is 1, C B dagger, which is 1, and B C dagger, which is minus 1. All the remaining commutation relations are trivial. So our algebra of operators is generated by X and P, just like in mechanics of a relativistic particle. Plus we have some internal degrees of freedom described by variables, canonically conjugated variables theta and theta dagger. So it's like collection of harmonic oscillators, but they are fermionic. So theta Grassmann parity is 1. This is an example where we have 2 degrees, Gauss degree and Grassmann degree, and they are not compatible. Then we have usual ghosts, just like in a relativistic particle we discussed. C and B, they are fermionic. So for instance, C is 1. And, let me change a little bit notation. Sorry, I want this to be, it's tradition to use, because these are bosonic ghosts. Let me, gamma and beta. Like this, and then there is no minus. Yeah, like this. Sorry, I changed, I forgot. And these are bosonic.
So modulo of C0 is 1, right? Because we don't have
It's not. It's my notation, short notation for Grassmann degree. It means that it's fermionic variable anti-commuting. If the Grassmann degree is 0, then commuting variables. If 1, anti-commuting variables. So C is fermionic ghost and gamma is bosonic ghost. Theta is fermionic variable, X is bosonic variable. So what is the idea? It's like a particle whose coordinate living in our 4-dimensional Minkowski space. And it's not just it's like a spinning particle, because it has some additional degrees of freedom described by this variable theta and its conjugated variable theta dagger. So it's not a particle, it has some internal structure. And in fact, with some additional constraints, it's going to be a particle with spin, a relativistic particle with spin. And we will see what it describes. And there are some constraints. And for these constraints, we already prepared and we introduced ghost variables, so that we can have, you see how many? We have 3 pairs of ghost variables, which means that we can have 3 constraints. So what are these constraints? Actually, if we want something simple and Lorentz invariant, because now we have a Lorentz symmetry acting on our Minkowski space and hence on our variables, it's not difficult to see what can be a Lorentz invariant combination. So one constraint is, of course, just mass shell constraint. In our case, it is the mass is 0. So this is just p squared, right? This is just p squared. This is clearly Lorentz invariant. And in fact, we have, it's easy to write two more quadratic constraints. One is a contraction of p with theta. It's convenient to use dot to denote invariant contraction of Lorentz indices. So it's p mu, theta mu. And another one is p theta dagger, which is nothing but p mu, eta mu nu, theta dagger nu. Like this.
Can we find these constraints without particular Lagrangian or Hamiltonian?
Pardon?
Can we find these constraints just looking at these commutators, like without Hamiltonian or?
No. I just defined for you Hamiltonian constraint system.
Oh, okay.
Of course, you see, you need to start with something. Often in the literature, people start with Lagrangian. But for this type of systems, honestly, it's just time consuming because Lagrangian is almost useless if you want Hamiltonian quantization. And once you have Hamiltonian, you immediately write down Lagrangian, right? Because we know what is a Hamiltonian action for constrained Hamiltonian system. But if you are given with like second order Lagrangian, it's still a bit of work to find constraints. You make mistakes on the way. It's boring, but it's much better this way. Unless you want like Lagrangian word-line formalism, then you need Lagrangian. But we do usual quantum mechanics, almost. Of course, it's not a physical quantum mechanics, right? Because it's not a Hilbert space, and it has different interpretation because we are describing relativistic systems. These constrained systems, they are either needed to describe something just as a technical tool, like for instance, normal non-relativistic particles living on some tricky spaces, and it's useful to represent them on constrained surfaces and use some technique coming from this BFV quantization to quantize them, for instance. But this is matter of mathematical technique. There is nothing deep. Or you want to describe relativistic systems. Then they don't have a genuine quantum mechanical interpretation in quantum mechanics, right? They only have interpretation in terms of field theory or other quantum field theory, but still they happen to be a nice tool to describe certain relativistic fields. And that's what we are going to see now. So I just give you three constraints. It's a simple exercise to make sure that these constraints are first class, right? Because if I commute this with this, the only non-vanishing commutator comes from theta dagger, and I get p square, right? So it's easy to write BRST operator, which looks like this. It's C naught p squared plus gamma p theta dagger plus gamma dagger p theta plus gamma dagger b naught. And here there is some coefficient which I need to look up, or you can check it. We can easily check it actually. So if you commute, we get gamma dagger p squared with minus, and no, it's even correct. I think it's with 1, just like that. Yes, it's just like that. Yeah, so it is nilpotent. It has, because these are Gauss variables, so degree 1, 1, 1, minus 1, minus 1, I mean Gauss degree, so it has right Gauss degree. So we have a BFV system, right? And we just need to specify our representation space, which we take to be again Fock space, which is going to be, well, not just Fock, it's going to be like functions in C naught and X, so wave functions, let's say.
The first sound in BRST junction with the p square?
Oh, yeah, p dagger, yeah, it's square. Yeah, sure. We don't have p dagger. Yeah, it's a typo. Sorry. Yes, h. So we take functions in C, not in X. I don't require L2 for some reasons now, but we can always change class of functions. Tensored with Fock space generated by all these pairs which contain like daggered variables. So just like before, variables with dagger are creation operators. Respective variables without dagger are annihilation operators. So we act with these guys, theta dagger, beta dagger, gamma dagger on our vacuum, and we produce states of our Fock space. So what we have here are polynomials in theta dagger, in gamma dagger, and in beta dagger. Right? So let's see when we act. So all in all, we can think of h as kind of wave functions in all these variables, right? It's the same. So it's very convenient to represent omega hat as a differential operator under our identification of our representation space with functions in X, C naught, theta dagger, gamma dagger, B dagger. We can represent our omega hat as a differential operator. So our omega acts in our representation space as follows. So what we have? We have C naught box, right? P squared gives us D'Alembertian. Gamma is d over d beta, so we get theta dagger p is d over dx, d, like this is just derivative with respect to, yes, like this, d over d beta dagger plus gamma dagger, and here we get d with d over d theta. And again, dot means contraction, invariant contraction of Lorentz indices. Plus, and here I get gamma dagger, d over d beta dagger, d over d c naught. Yeah, that's what it acts. That's how it acts. So you see this piece, you can think of this, because thetas are fermionic, you can think of functions in x and theta as differential forms. So this is like the Ram differential. This is like divergence operator in these terms. Sorry, this should be dagger. Yeah, and that's it. Yeah, well, that's what it looks like. To understand what it describes, it may look at first glance a bit involved, but in fact it describes quite a simple system. So let's also introduce kind of operator which commutes with omega and which simplify our analysis. This n looks like this. It's theta dagger d over d theta dagger plus gamma dagger d over d gamma dagger plus beta dagger d over d beta dagger. It's like certain homogeneity degree, total homogeneity degree in these variables. And in fact, this n commutes with omega. Why? Because you see each term has a vanishing homogeneity in these variables. Clearly, first commutes, right? Second, you see you have one derivative with respect to daggered variable and multiplication by daggered variable. So the overall degree is 0. And here's the same, gamma dagger d over d b dagger. And again, here's the same, gamma dagger d over d beta dagger, right? So this clearly holds. And this again simplifies life for us a little bit because we can restrict. So this is like a conserved charge in this system. So we can study our system step by step. We can decompose our H into eigenspaces of different eigenvalues with respect to n. And of course, everything inside this subspace doesn't talk to other subspaces. So it's enough to analyze one. So let's analyze, for instance, the following subspace, that n psi equal to 0. So this is a kind of trivial step. trivial case. So what happens? What is a generic state which satisfies this condition? The state from H, vector from H. So it's psi, which is equal. So you see, all these are daggered variables. They are not allowed. So we only have C naught and X. So generic state looks like this. It's phi of X, phi naught of X, plus C naught phi 1 of X, right? All other terms are not allowed. So it pretty much looks like a state for scalar particle, for spin zero particle, right? And for instance, if we write, do you remember that we can write introduce inner product, which is just integral dc naught and Fock space inner product, and we can now write and also integral over Minkowski space, of course, d for x. So we can do here, we can write something like this: psi omega hat psi. All these terms can't contribute, so only this term contribute. So we get integral d for x phi naught box phi naught. So it's a Klein-Gordon action. So it's a right action for our scalar particle. But this is only one sector of this model, where n acts trivially. It's a small subspace in our representation space. And if we restrict to this subspace, we see that what we are doing, we are describing scalar particle, spinless particle, right? Just Klein-Gordon Lagrangian with zero mass. And note also that if you have an action like this, your equations of motion are just omega hat psi equals 0. If you vary with respect to psi, take into account that inner product is non-degenerate, you get this equation. So the condition that your state is physical is an equation of motion of this action. Okay, let's. This was completely trivial.
Why do we call it the action or
Because one of possible interpretation of relativistic quantum mechanics is that in fact it's linear field theory, and if we work in these terms, the way to produce the respective action is like this. Because like you see what happens. Solutions to these equations
are the physical state?
As the physical states. Yeah, that's what we have in field theory.
That's why we call it an action, because these equations of motion.
Yeah. Okay, next example. So let's take n equal 1. What happens in this case? In this case, our psi can start to depend on these daggered variables, and it must depend to produce this one. So psi may look like what? And we also let's require also ghost of psi to be like a physical state. Ghost of psi equals 0. And Gauss degrees are assigned in a natural way, just as a Gauss degree of a polynomial like this, right? So you just count how many ghosts enter, what are their degrees, and you get the degree. So what can appear in this formula? So first of all, so we need one daggered variable. Without it, it doesn't work. So what we can have? We can have something like C naught beta dagger B of x plus theta dagger mu, let's say a mu of x. What else can we have? We can have also gamma dagger something But if we have gamma dagger, we need to compensate the Gauss degree 1 with something, but the only variable in negative Gauss degree is beta dagger, so it doesn't enter. So that's all we have. So that's the generic form of psi of Gauss degree 0, and this charge equals 1. And in this case, you can again construct action. So think of this as fields of B and A mu, which is just psi omega hat psi. And
why is the Gauss degree of psi 0? Wasn't the Gauss degree of beta and
yeah, this is 1, this is minus 1.
oh, minus 1? Okay.
Yep. Because it's like momenta. It's momenta for gamma ghost.
Why cannot we have here something like gamma dagger B0?
Because B0, do you see here B0 in your representation space? You don't. It's like momenta in this representation.
Why not gamma dagger?
Gamma dagger has degree 1. You need to compensate it with something. You can always only compensate it with beta dagger, but this gives you n equal 2. Okay, so this is an exercise. Any guess which field does it describe? Pardon? No. Do you see fermionic fields here?
Vector field.
Yeah, it's Maxwell. And if you go to, well, second point, if you want to play a bit more, you can do n equal 2, and this is going to be what's called two-form gauge theory. Yeah, one last remark. So it's an exercise to play with. So you see we already described gauge fields for free. And the last remark exercise I gave, the last remark is to, you see, equations of motion for such an action is omega hat psi equals 0. But in fact, this data also knows immediately gauge invariance, because you can see that if you transform psi to omega hat on some chi, and Gauss degree of the element chi is -1, then because omega is nilpotent, this equation is preserved, right? Same way this action is invariant under such a transformation. So in fact, this omega, if we interpret it like this omega hat, it knows about equations of motion of a certain field theory, and also it knows about gauge symmetries of this field theory. And this becomes important here because already in this case we have actually a gauge field, because there will be non-trivial gauge parameter because we have B dagger. And but what is why I suggest to do this exercise? You see, this action depends on two fields, on vector field A mu and on scalar field B. But we know that Maxwell, the action should depend on A mu. But here it depends on additional field B. So it's interesting to check that everything is actually okay, that it's a slightly different form but equivalent of Maxwell-Lagrangian. And more involved exercise is to consider n equal 2 and to make sure you indeed describe two-form gauge theory where your field is just two-form antisymmetric tensor of rank 2.
Sorry, and are there any ways to fix this model to like give extra fermionic degrees? So why can't we see Dirac equations?
Yeah, it's also possible, but you just need additional variables. You can describe all possible fields in this way. Yeah. Gauge fields. Yeah. But if you have gauge fields, you also can describe massive fields through dimensional reduction. That's a standard mechanism in Minkowski space. Okay. So much about these quantum BFV systems. Interesting ones, as I said, are relativistic, and they have their interpretation more in terms of field theory. By the way, this is precisely the technique how people construct field theoretical interpretation of string theory. This is what's called string field theory, where as a underlying quantum constraint systems, one takes quantized string, wall sheet theory, builds analog of this, finds interaction because it's quadratic theory, but in the case of string theory there are some natural interactions to add here, and the resulting system is known as a string field theory. It's of course it's debatable how useful it is, but still people actively studied it at some stage, and even now they continues to study with some hopes to improve. Okay, good. So we need to proceed, and now we finally get to what BV is. BV at classical level. Let me remind you that if we have a constraint system with space, first-class constraint, we're only talking about first-class constraint systems now, with phase space M naught, we have symplectic structure, Poisson bracket, whatever you prefer. Then you have Hamiltonian, and you have constraints T alpha. Then we know what is physical interpretation of this system, and we know that we can also describe it as a specific first-order Lagrangian system, which is called extended Hamiltonian action, and which looks like this. So all the dynamics is encoded in this action. So Z are all my phase space variables, and these are components of symplectic potential. So it's roughly speaking PQ dot in mechanics, minus H naught of Z, minus lambda alpha T alpha, and all this is dt, right? Usual action in mechanics. And it depends on, so it's a functional of Z and lambda, of configurations of Z and lambda. Z are all my phase space variables, P and Q usually, and lambda are Lagrange multipliers. But now we learned that this data can be effectively rephrased in terms of BFV system. Which is now extended phase space M, again extended symplectic structure, let me write it like this, X, then extended Hamiltonian, which is H naught plus possible ghost corrections, and this BRST charge omega. We are back to classical level, omega, right? And one might ask the following question. Is it possible to kind of find an analog of such an action which is built immediately in terms of this extended data? Of course, inside omega you can find T alpha, inside H you can find H naught, etc. But suppose you don't want to go inside, you're just given with this, and you want to find a kind of action which reproduces this. It's a little bit strange question. But in fact it has a remarkably simple answer, and this answer points us to what BV formalism is, and the answer looks like this. So let's introduce new variables and call them Z star A. Now I use capital Z with capital A index to denote all coordinates here. So ZA are all coordinates. Our phase space coordinates plus ghost coordinates. They are all now denoted like this. And then we introduce like conjugate momenta to them. But these conjugate momenta are not usual. Their degree is different. So ghost degree of Z star A equals to minus Gauss degree of ZA minus 1. So if it were usual momenta, just like in our Hamiltonian formalism, then we wouldn't have this minus 1, right? We just need to prescribe our momenta the opposite Gauss degree, and if we also have independent opposite Grassmann degree, so that the bracket is a gain of degree 0. So it's like Z and Z star are canonically conjugated. But now we change it. We shift it by 1. So it's like odd momenta in a way. Okay? Yep.
But in order to do a separation, to get back to the our initial system, can we just kill Gauss degrees? Like if we have Hamiltonian H or omega, can we just kill everything?
Yes, we can. Yes, yeah. We can always set to 0 all variables of non-vanishing degree. It's called body of our graded manifold, and of course, when we restrict H to the body, it's going to be H naught, right? But we want to do it differently. We don't want to do it like by hands. We want to keep Gauss variables, and we want to write something which will reproduce it. The logic may appear strange, but surprisingly, it's an interesting trick, and it quickly gives us BV formulation of the system. So, okay, so we introduce this, and then we can write, in terms of this data, we can write action of this structure, which in fact reduces to this one if we set, precisely as you said, if we set to 0 all these Gauss variables, all variables of non-vanishing degree. And the action looks like this. So let me call it BV, because it's the first example of BV master action. It's again integral over time. Here we have chi x, which is a symplectic potential for the extended symplectic structure on our space of phase space extended by Gauss variables. So this, just to give you an idea, so this omega x is something like typically dp dq plus dp dc. So it's a symplectic structure with contribution from Gauss sector. But in general, of course, there can be many generations of Gauss, and this can be tricky, but this is the idea. And this is just a potential for this. So p dq plus pi dc. Okay, A, z dot A minus h of z minus z star A z A omega. That's it. So in fact, if you think what can you actually write, because you want something of degree 0, right? You want something where all indices are contracted properly, something first order starting with usual symplectic term. Maybe it's difficult to write something else, right? And which contains all the information. Okay, so this is, strictly speaking, it's not clear how to interpret this action, because this action depends not only on our phase space variables, small z, or pq, but also on Gauss variables and Gauss momenta. So it's a very strange action which depends on variables of different degree, although the overall Gauss degree of this SBV is 0. So it means that there is inside there is a piece which can be a non-trivial and which can be Gauss independent, right? And that's exactly the case. So the simple statement is that if we set in this BV all variables to 0, so like we C, P, how to write this? Okay, maybe let me say it by words. I don't know how to write it. So SBV where we put all coordinates to 0 if ghost of psi is non-zero. So we only keep coordinates which are of degree 0. All the rest we set to 0. And then this is equal to SH. So or more mathematically, the restriction of this action to the body of the manifold, well, the shifted cotangent bundle, because it's M plus Z star, this restriction is precisely this action. Let's check it. Let's take the simplest setup, because this action is written in the simplest setup. So let our omega be C alpha T alpha plus higher resolution degree terms. Our H is H naught plus high resolution degree terms. And let's see which variables do we have in degree 0. So of course we have ZA, they are all in degree 0, our initial coordinates on our initial phase space. C, our ghost C alpha is of degree 1, so we should forget about it. But the same with ghost momenta pi, but what is interesting that our ghost momenta is of degree -1. And its conjugate, this is called antifield in fact, usually. This conjugate antifield for ghost momenta, if this is -1, if this is -1, then this gives 1, -1 gives 0, right? So there is variable P star alpha, which is an antifield conjugated to ghost momenta, which is of degree 0. So this is of degree 0, this is of degree 0. And actually that's it, because Z star is going to be of degree -1, pi itself is of degree -1, and C alpha is of degree 1. So the only variables of degree 0 are these guys. And look that this guy looks precisely like Lagrange multiplier. It has exactly the same index in the right position. And in fact, this is precisely it. So if we now continue this equality here, so what is this SBV, where we set to 0 all fields of non-vanishing degree. So it's easy to see that from this guy you only get ZA, because ghosts do not contribute. So we get back our chi A Z dot A, right? From this we only get H naught. And let's be careful with this. Among the variables with, sorry, it should be the other way around, star A, it's nicer like this. Among these variables, among these antifields, only antifield conjugated to ghost momenta pi is of degree 0. All the rest terms vanish in our consideration. So here we get this pi star alpha times bracket of ghost momenta with omega, after which we set to 0 all, after evaluation of this bracket, we must set to 0 all variables of non-vanishing degree. But this bracket, if we compute pi alpha with omega, this is of course nothing but T alpha plus some ghost-dependent terms which do not contribute anyway. So what we get here T alpha, right? And this is precisely this action under the identification that the antifield conjugated to ghost momenta pi, this pi star alpha, is to be identified with the Lagrange multiplier. So there is something interesting happen, because we don't, if you play this game, of course we have more variables, we need to take care about other stuff, but now we don't need to introduce Lagrange multipliers by hands, because before we had to. We had our space, we had our phase space, we had our constraints, and then to write down action, we should have introduced, we had to introduce Lagrange multipliers as extra variables. Now, they automatically appear from this systematic extension. We don't need to know like how many of them to introduce. We just introduce these antifield variables z star a conjugated to all our extended phase space variables. And among them, you precisely, in degree 0, you precisely find Lagrange multipliers. So, which is probably a good sign. So, we know how to extract this action without digging into the structure of inside the details of omega and h, right? We just do it systematically. We introduced odd momenta for all variables, we write down this natural formula, and then we set to 0 everything which is in non-zero degree, and we recover our initial action. But it turns out that even without setting to 0 variables of non-vanishing degree, this action is quite interesting, and this is precisely what is called master action of Batalin and Vilkovisky. Okay. So what are its properties? So first of all, we have new structure. Let's discuss it a little bit. Because we introduced momenta, these odd momenta, which are usually called, as I said, which are usually called antifields, these z star variables, it's clear that we should have some kind of new Poisson-like bracket, right? Because when we have certain coordinates and we introduce conjugate momenta, then we have a Poisson bracket. Now we introduced like momenta, but these are momenta with shifted degree. So we have odd Poisson bracket, and historically it was called anti-bracket. Now people use this name less and less because they discovered many brackets, and this is just one of particular examples. Odd Poisson, or shifted sometimes Poisson bracket. And strictly speaking, it's better to immediately define it on the space of like field histories, so on the functionals, because now we are in one-dimensional field theory setup. Of course, this index itself can hide spatial index, and it can well be a field theory, but let's pretend we do mechanics for simplicity. So what the bracket is, we define it for two functionals to be just like Poisson bracket in field theory. I explicitly say how derivative act, what are right and left. And let me erase and continue here. So standard thing, sorry, df over dz star a. Now I write variational derivatives because it's I define this bracket on the space of functionals. D z a, right? So because degree of this and degree of that is shifted by 1, so the degree of the entire bracket, so ghost of fg is ghost of f plus ghost of g plus 1, right? So it's a bracket of degree 1. Our usual Poisson bracket in the graded setup had degree 0, which means that it doesn't add or subtract any degree, right? So the degree of a bracket of two functions is a sum of degrees of the functions. But now there is additional 1. This comes from the fact that this momenta, this odd momenta or antifield, has a shifted degree with respect to this one. Another way of writing the same is just to say that za of t with z star b of t prime is delta ab delta function of t minus t prime, right? Just like we do brackets in field theory with delta function. And now from this, of course, you can get this using the standard formula. What are properties of this bracket? It's again kind of Poisson bracket, just with some fancy symmetry properties. For instance, the symmetry property like this looks like this: Fg equals to minus 1 to power f plus 1 g plus 1 gf. So if we exchange, we get a funny additional sign factor, and Jacobi identity reads like this. So the best way to remember Jacobi identity is to think of it as that a bracket with something differentiate another bracket, satisfies like Leibniz. So what we can do, we can write this. So think of taking bracket with f, which is a Hamiltonian vector field, in this case, of course, in the sense of odd symplectic structure or odd Poisson bracket. It's like taking bracket with f is a differential operation, which goes like step by step on all ingredients, and it satisfies, Jacobi means that this operation satisfies Leibniz rule, which means that what we get Fg with h, and then we get a second term, which is, but here we get a funny sign factor because this bracket with f. And remember, bracket carries degree 1. So it's like an object with this operation of taking a bracket with f carries degree 1 plus degree of f. So we get minus 1 to power degree of f plus 1. And then it should go through g, but in fact the bracket itself also has degree 1. So somehow here you get g plus 1, this factor, and here you get g f h, right? So it pretty much looks like a Leibniz rule satisfied by this operator of taking bracket f with the argument. But the only thing to remember is this sign factor, which is easy to remember because this sign factor means that like bracket together with this, and bracket carries 1, like 1 plus degree of f, and here 1 plus degree of g because it also like goes through the second bracket. That's it. So it's like graded Poisson bracket, but with different assignments of degrees. But with this, if we look at this equation, what we observe, there are two, well, on this and this, there are two algebraic consequences. First of all, if degree of f is 1, then it means automatically that ff is 0. So do you remember, in the case of usual Poisson bracket, if we had a fermionic element, such an equation could be non-trivial, right? Like omega omega, for instance. But now this equation is trivially satisfied, just like in non-graded case, right? But what can be non-trivial, if degree of f is 0, then ff, if we exchange, we can't play symmetry, because if f is 0, here we get 1, 1, so minus plus additional minus gives plus. So we can't use symmetry to prove that it is 0, so it is non-zero in general. So there can be an equation analogous to the BFV master equation, but now for the object of degree 0, and which look exactly the same. And another algebraic consequence, if you look at Jacobi, you can find that f is identically 0. Of course, it is identically 0 if f is fermionic, just because even this argument is 0. But if f is bosonic, although this is not 0, the triple bracket, the double bracket is 0. Okay, and let's examine this equation. what is FF, where instead of F we put our BV action. And this, let me see how much time do we have, not much. So let's do it as an exercise then. So SBV, so one needs to compute it. And it turns out that it equals to integral dt, total derivative of something. So the exercise is to obtain this, and in particular to find what is inside the brackets. Which means that if we impose proper boundary conditions, this is a boundary term, right? We get 0. Which means that given the proper boundary conditions, our master equation is satisfied. And this is satisfied on account of this. So you see what happens. We had these defining equations in the case of Hamiltonian formalism, and they, through this construction of SBV, guarantee the master equation in BV formalism. In fact, what we met is a special case of BV formulation. So this is a good and instructive exercise to play with. Okay, in the remaining few minutes, let me try to explain what this BV action look like in terms of components and what is its meaning. So for this, we for the moment forget about this specific BV action. We only remember what are properties. So we know that SBV, so like axioms, what we have, so the logic is as follows. We arrived at something particular, starting from first-class constraint system. We reformulated it using BFV formalism. Then we constructed out of it certain Lagrangian formalism with this SBV, with anti-bracket, everything. Now we want to look abstractly at what we arrived at, formalize it as axioms, and then say that, okay, general BV is something like this, where all axioms holds. So what are axioms? So first of all, we have field-antifield space. And for the moment, I'm even going to forget about explicit time dependence. I'll treat everything as if everything were finite dimensional, just to make things more transparent. Field-antifield space. So I have some fields, let's say psi A, and their conjugate anti-fields psi star A. And they are canonically conjugated in anti-bracket. So anti-bracket tell me that psi A, psi star B is equal to delta AB. If I want to recover this explicit time dependence everything, I should remember that A is actually a condensed notation, so it's an index plus time or plus space-time, and this delta symbol contains also delta function. But for the moment, let's don't concentrate on these field theoretical difficulties and pretend as if our space of fields were finite dimensional. Okay, so anti-bracket, what else? Then we have SBV, which is S naught of, let's say, physical fields, which are found in degree 0, physical fields, plus like psi star on something. So further terms already, not a good idea, because this can be also physical, plus, let's say, Gauss depend. Well, terms proportional to So terms which vanish when we set to 0 all fields of non-vanishing degree. So that's what we found. Our BV action, which we arrived at, we just gave it a name, anticipating something, looks like this. It's a usual physical action, for instance, in our example, extended Hamiltonian action of a first-class system, plus some extra terms, but all of them necessarily depend on variables of non-vanishing degree. So if we set to 0 all these extra variables, we are just back to our initial physical action. And this SBV, so well, maybe it's better here, GOST SBV is 0. And important thing is that it satisfies master equation. Of course, we saw this, but we want our boundary conditions to be proper in order to ensure that if we really do everything properly, we get 0 here. So this is BV master equation. BV master equation. Okay. For the moment, that's it. So that's what we observed on this example. So let's use this as a definition of BV system. So we say that actually what we observed, we take as a definition, and let's consider generic BV system. So this definition, BV system, this list of data and axioms. Okay, and exercise, we will start next time with it. So consider the setup where we have coordinates phi I of degree 0, coordinates C alpha of degree 1 and their antifields, which means that we have phi star I of degree -1 and we have C star alpha of degree -2, right? Because this is 1, the rule is -1, so it's -2, it's -1. This is determined by properties of the anti-bracket. So suppose that we are in this setup. So our field-antifield space splits into, so there are fields of degree 0, ghosts of degree 1, and their conjugate antifields. So find, of course we can then extend, we can expand our S as S naught of phi plus something like phi star I Ri alpha C alpha plus higher terms in ghost expansion. For instance, there can be a term like this. It can be phi star compatible with degree phi star j, mij, in principle depending on phi, alpha beta, C alpha, C beta, plus more. So in the exercise, so I just wrote a generic first terms of generic expression of this expansion of S with respect to the variables of non-vanishing degree. And what I ask is to find, let's say this is BV, BV, BV. What does it imply in terms of S naught, R, M? Of course, there are higher functions, higher structure functions, but let's don't discuss them, but these are really physically important. So what are the relations between S naught, R, this is also a function of phi in general, and this mij alpha beta, which are also functions of phi. If all phi's are bosonic, then this guy is antisymmetric in ij, right? Because these guys are anti-commute, and antisymmetric in alpha beta, because these guys are anti-commute. So what are the relations between S naught, R, and M, which are encoded in this equation? So just expand this equation and see what conditions do we get on these coefficients. So this is an exercise, and I'm afraid we have to stop here, and we continue next time.